Okay, so first of all, thank you very much, Bruno, for the introduction, and I thank you and Vitorita, others in the organization committee for inviting me to give this series of lectures in this beautiful place. It's a pity, I should have recorded you, Bruno, because then when I am caught by the guard, I will just play this recording and say that I was authorized by Professor Dupre. So anyway, so before I start my lectures, which will be on operator learning, as you can see right here, operator learning, which has emerged as a, let's say, one of the leading topics in what is called a scientific machine learning, even though I don't like the term very much, but nevertheless. So let me start with some rules of thumb so that we set some rules to begin with. The first is my lectures are going to be sort of not too much of detail, a lot of heuristics, a lot of, let's say, hand-waving arguments, no detailed theorems, no detailed codes and so on, because I feel that in this format where I have 4 hours to lecture, the best thing is to sort of give you ideas, expose you to a new topic, and not drown you in details. So if you need precision, you can ask me later or you can look at the papers. So that's the first rule of thumb, that I will be very heuristic and just try to give a gentle introduction to the topic. The second rule of thumb is that I came only yesterday night, so I haven't followed the lectures that Olga and Jin Shao. I see Olga somewhere, yeah, but I don't see Jin Shao. I haven't seen the lectures, so it could be that some things are repeated, but then remember that repetition is always a key to success. So it's not a bad thing. If I repeat, it's a good thing, right? So then we're all on the same page. So that's the second rule of thumb. The third rule of thumb, which is very, very important, is that please do interrupt, please do ask questions to me, and I really appreciate that. The easy questions you can always ask me. The difficult ones, please reserve for these two gentlemen who are here, Emmanuel de Bezenac, Dr. Emmanuel de Bezenac and Roberto Molinaro, and they are going to help you with the exercise session later today. So just the easy ones ask me, and difficult ones are directed at them. So now with these rules of thumb, let us start the topic, which is about operator learning. And let's see. Okay. So what are operators? Now, if you are from a math background, it's very clear what operators are, but not everyone is from a math background. So let me spend a bit of time trying to explain what operators are. So operators, roughly speaking, everything is heuristic and hand-wavy. So roughly speaking, operators are mappings which take inputs from an infinite dimensional space and land you in an infinite dimensional space. So a mapping between, let's say, a function space to a function space, a sequence space to a function space, a sequence space to a sequence space. So these are sort of operators. So they generalize our understanding of functions, because think of it. So when we consider a function, for instance, the temperature in this room, so what are the inputs to that? So these are the coordinates, wherever you are sitting, the x, y, and z coordinates, and time, right? And given these 4 numbers, you produce another number, which is going to be the temperature. So in this case, it's a mapping from R4 to R, right? So that's why it's a function. An operator, on the other hand, would be, for instance, temperature now as a function. So we give the temperature as a function, and what is the temperature after 6 hours? So we know that we take a function and we map it onto a function. So we know that it will be much hotter. So that is a very easy, at least we know the direction. So an operator is a mapping between functions and functions, between sequences and sequences, and so on. So the most canonical example of an operator that you can think of are, for instance, the derivative, right? So you take a function which is continuously differentiable, and you take its derivative, it lands in the set of continuous functions. So that's an operator, the derivative. Similarly, if you take the weak derivative and you consider Sobolev space Hs, then the weak derivative takes you from Hs to Hs minus 1. The weak second derivative will take you from Hs to Hs minus 2, and so on. Or the antiderivative, or the primitive, that will take you from Hs to Hs plus 1. So these are sort of canonical examples of operators. In physics in general, the sort of another canonical example of operator is provided in quantum physics, right? So in classical physics, it's enough to describe the properties of a system, the state of a system, just by giving coordinates, space and time, and then you describe the state of the system, temperature, pressure, velocity, and so on and so forth. But in quantum physics, on the other hand, we know that coordinates are wave functions, right? So they tell you the probability of a object being in a certain configuration. So we have wave functions, and now the inputs are the wave functions, the outputs are, for instance, the kinetic energy, the potential energy, and so on. And these are defined in terms of, for the entire Hamiltonian for quantum dynamics is explained in terms of the so-called Hamiltonian or Schrodinger operator. So this is sort of a non-trivial example of an operator coming from physics. But for my purposes and for the purposes of the rest of the talk, the most important class of operators that we'll focus on are solutions operators of PDEs. So I have given you two examples of PDEs here, and let us try to infer what the solution operators are. The first is the standard diffusion equation. If you want to consider, say, electrostatics, or if you want to consider fluid flow, this is called the Darcy equation. So you have, this is the equation here. So for instance, if I fix the source term f, then the mapping that are the input to this particular PDE, and also I fix the boundary condition, the input to this particular PDE is given by my coefficient A. Now this coefficient can, for instance, be the conductivity if I am in electrostatics. It could be the permeability if I am considering flow in a porous medium, and so on. And then the output of the system, so this is the input, and the output of the system is going to be the solution of the PDE, right? So the mapping or the solution operator in this particular case is a mapping from L infinity bounded functions, bounded positive functions, for instance, to H1 functions. So this is, for instance, the mapping that we are describing. So the mapping between the input, which is the coefficient, and the output, which is going to be the solution of the PDE, the conductivity, the voltage, for instance, or the pressure head. So this is going to be the solution operator, and as you can see, it's a mapping from an infinite dimensional function space to another infinite dimensional function space. Another example for time-dependent PDEs, so it's just one particular proxy. It can be any equation that you want. So what I've described here are the compressible Euler equations. I don't write them down. But so this is the initial condition, the initial density, which is given in these colors here, and the initial velocity, which are given by the arrows. And the solution operator is a mapping which takes the initial conditions, which are, for instance, in the space of functions of bounded variation, and it maps to something which is in L infinity. So this is the density at a later time, or you can consider the whole trajectory of the solution as a function of time. So again, the operator here takes the initial conditions. Yeah?
Perhaps the sound of your computer is still on. So for the quality, better to...
Okay, sorry.
Could you check? Good.
Now it should be okay. Okay, so this is another example of a solution operator that you take the initial conditions and it churns out the solution at a later time. In both these cases, and for any PDE that you can think of, the inputs to the PDE, initial conditions, boundary conditions, source terms, coefficients, and so on, and the output of the PDE, which is the solution of the PDE itself, these are the mapping that connects the inputs to the outputs is the operator, is the solution operator. So solving a PDE essentially is tantamount, amounts to finding the operator. And since we can only find exact or analytical solutions as rarely as a needle in a haystack, so what we have to do is we have to somehow approximate a PDE, which means that we are approximating an operator. So this is the context that I am operating in, that for me, I reduce the problem of solving a PDE to approximating an operator. And this is the first message that we can take out from here. That's why operator learning is important. Of course, it has other applications in physics and in inverse problems and so on. But in the numerical solutions of PDE, the main point here is the fact that we have a solution operator and we need to approximate the solution operator. Okay, so now how do we do that, right? How do we do this operator approximation? So this, now for some reason I'm not able to, okay. Oh. So traditionally we use, or it's not traditional, we still do them all the time, is we use numerical methods, right? So we know that we can't find an explicit solution formula, so we need to find numerical methods to solve the PDE, and they are in different guises. You have finite differences, finite volume, spectral methods, finite elements. There's a whole zoo of them. There are many people in this room who have contributed and even pioneered the development of these methods. And for time stepping, for instance, you can use Runge-Kutta and so on. And the point is, these traditional methods, these are also operator approximation methods because they are approximating the solution operator of an PDE. And we know that these are very, very successful. And these are some, again, I'm sort of struggling a bit. Yeah. So these are some examples from my lab. We used numerical methods, finite volume, finite difference, finite element methods, for instance, to do core collapse of supernovas, to simulate clouds, to simulate rock slide generated tsunamis, flow past rockets, and all kinds of exotic things. And each of you, in some sense or the other, could use them, traditional numerical methods, to solve these kind of complicated PDEs. Now, the point is, so we should remember, and this is not for nothing, that traditional numerical methods work quite well. And whenever we are designing some alternative, we have to benchmark our method against traditional numerical methods to see if we have an advantage, a competitive advantage. If not, we are not doing the job, right? So this is a very, very important perspective that one should keep in mind. But of course, otherwise, I would have stopped right here and we could have all gone and taken a swim in the Kalank. So there is something, there is an issue with them. And there are several issues with these sort of, let's say, traditional numerical methods. I don't like the term myself, but I couldn't find a more befitting term. And the first issue that we could think of is, of course, computational cost. All of you have seen that they tend to be on the more expensive side. Depending on the application, they tend to be on the more expensive side. And this is particularly seen when you have what are called many query problems. I think they have probably been introduced to you. Many query problems are those where instead of solving the PDE once, you have to solve it 10 times, 100 times, even 1,000 times, tens of thousands of times, and so on. And these many query problems come in a variety of ways. You could have uncertainty quantification, design, PDE constraint optimization, optimal control, inverse problems, both deterministic and Bayesian inverse problems. And all these problems, the objective is that, or the method that we use is to solve the PDE again and again and again, so that the whole thing becomes very expensive. Let me give you an example. So up here is a sample, a realization of a compressible turbulent flow. So this is the compressible Euler equations solved at very high resolution. As you can see, it is essentially 1 billion mesh points, and there are also 1,000 time steps at least, or 10,000 time steps. So it's like a very, very big problem. So a trillion or 10 trillion degrees of freedom, if you want to think of it like that. So this is a simulation at a very high resolution of a compressible turbulent flow. And it was expensive. It was quite expensive. It was done on we used several years, 5-6 years, to design a sort of a GPU-based code which did this simulation. But the point is, since it is a compressible turbulent flow, it's very difficult with one realization of the flow to get any meaningful information, because one realization, it's sort of very sensitive to initial conditions. If I change them slightly, I get a completely different flow. So I need to do some uncertainty quantification here. I need to compute quantities like the mean and the variance. And for that, at the moment, you have to do Monte Carlo simulations. Nothing else works in this regime. So if you do Monte Carlo simulations, you have to do this 500 to 1,000 times. And when you do this 500 to 1,000 times, each simulation itself was very, very expensive, something like 500 to 600 node hours on one of the largest supercomputers on Earth, which is there in Lugano in Switzerland, where we have access to. And if I would have done this, or I did this 1,000 times to compute the mean and the variance, and coming from Switzerland, where everything has a price and everything has a cost, they even give you a number. They said that this entire simulation, which is an ensemble simulation has been done again and again and again, it cost you $1 million US, okay, or 1 million euros, if you want to think of that. So this is very expensive, and just imagine if you keep on doing these kind of simulations, then the expense is just incredible. It's prohibitive. So you cannot do certain things. For instance, if you want to do Bayesian inversion using a Markov chain Monte Carlo, an accurate method, Metropolis Hastings type method, then you need 10,000 simulations in serial, in sequence, and you cannot afford that. So at some level, particularly in 3D with multiphysics problems, there is a limit to it. So this is one thing that we should remember all the time. The second thing that we should remember is that there is a human cost. I don't put it on the slide because, but there is also a human cost to these things. The amount of man hours or person hours that are spent are just among us. So just to design this code took us many, many, many years. So there is also a human cost to this. But there is also another element that is sometimes not as prominent, which is that not always does the PDE that we have, the physics that we have, describe the system properly. And I will give you a few examples of that. I don't know how well you see them. So this is a typical example of a reservoir simulation, actually done here in France. So typical example of a reservoir simulation. Now, anyone who does reservoir simulations knows that the physics that is used to describe them, the equations of two-phase flow, three-phase flow, and so on, these equations, the physics there is extremely suspect. Means we do the modeling in a very, very approximate manner, and we know very well that there is a limited validity to these equations. So for instance here, okay, we have a nice picture, a nice simulation, but who knows how correct the physics is. So there is some missing physics here. And then if you go more towards biological applications, for instance, this is blood flow in the brain. These are some snaps of it, blood flow in the brain. Again, means biological quantities, who knows what is going on there, what are the scales, and so on. So there is a lot of physics, and not all of it can be just undetermined parameters. Not all of it can be fit in terms of undetermined parameters. There could be, for instance, really missing physics. And the final example is from a traffic simulation in the city of Zurich. I work with a startup which does it. And there, of course, the physics is really fake in some sense, right? Because who knows what are the rules that traffic follows. Maybe in Zurich, they follow very different rules from here in Marseille. And certainly from where I come from, the rules of traffic are very, very different. So there is no physical description. I come from India. So the rules of traffic are going to be very, very different. So certainly in all these examples and in many, many more, the PDEs that we have to describe the system, they might not have, the physics might not be complete. There is some incompleteness in the physics. So these are some of the issues that are there. Either it's expensive, or it's probably not a good determination, not an exact, accurate determination of the system that you are considering. There is also a third element, which is, or another element, which is sometimes missed, which is that whenever we do simulations with PDEs, the usage of data that we generate, the data that we throw in, the data that churns out, that I would call is inefficient. What do I mean by that? For instance, let us take this simulation. Suppose I take this simulation, I perform the simulation, it was a very expensive one, right? As I said, several trillion total degrees of freedom. And then what do I keep? I just throw everything out for the next simulation. When I take a different initial condition, I just keep some statistic perhaps, but I essentially throw it out and I start again. You see, so each time I do my simulation, I forget what I have done in the past and I start again. So the data is completely forgotten. Okay? And this is sort of an inefficient use of data, because we are in a regime where we believe that the physics can give us all the information. Each time I throw a ball, I start with my initial conditions, I use Newton's laws, and I calculate the trajectory. The fact that I have done this 1,000 times or 1,000,000 times or 1,000,000,000 times is useless, or is just thrown out of the picture. So in that sense, there is an inefficient use of data. I generate a lot of data, which I'm immediately writing out, right? So this is something that we should remember. This also gives us, so these kind of issues, they tell us that business as usual with traditional numerical methods, there are certain limitations. And there is a possible way out. One has to qualify that a little bit. There is a possible way out, which comes from the fact that we generate so much of data, we have access to data, particularly these days. And if we are able to efficiently use this data, then maybe we will be able to solve some of these problems. Maybe it's a question. We'll see how far we get. So now this provides the context for what I'm going to say for the rest of my lectures, which is that we are going to remember that at the end of the day, again, I'm struggling a bit here. At the end of the day, at the end of the day, I want to approximate an operator, and and I want to use the data in order to approximate the operator. Of course, I also would ideally like to use the physics. So by combining these things, my objective is to learn operators from data, and in particular, sort of contextualize it within the context of numerical methods for PDEs. So this will be the objective, and now I gave you the rationale for this objective. Are there any questions so far? No? Okay, so let us move on. How do we learn operators from data, and what exactly is the problem, right? Okay, so again, I'm struggling. So how do we learn these operators from data? Okay. So this is, the answer is somehow there, means we all, this is why this summer school is there. So we know these days that we are in the age of machine intelligence, and with machine learning there have been all kinds of exciting, even magical sort of breakthroughs, whether it comes to AlphaGo, where a machine learning algorithm managed to defeat the champion Lee Sedol in Go, or AlphaFold, which is now used heavily in structural biology and chemistry, where one algorithm, AI-enabled or AI algorithm, has been able to solve protein folding, which has been a very vexing problem. All of us have used ChatGPT, I am sure, and all of us have seen this fake picture of the Pope wearing a puffer jacket. So all these are sort of iconic successes for machine learning. And all these successes, in my opinion, they rely on 3 pillars. Okay, could be more, but at least on these 3 pillars. The first is that they use exponentially more compute, or also called as GPUs these days. But so now we have access to much more compute than we had before. We can, of course, use them for our traditional numerical algorithms. Means no one stops us from doing that. But machine learning algorithms run on and should be able to use this compute that is available to us in an efficient manner. The second point, which is sometimes not considered as important, is that you need huge amounts of data. All these things, for instance, ChatGPT was trained essentially on the whole internet, right, or Common Crawl as it is called. So there was lots and lots of data. Now, in general, this is an issue that we have to confront with at some point, because a priori, it seems like we don't have, and I'll try to explain that in a bit, that we don't have such high quality of data, and somehow we have to increase the amount of data that we are generating, or the amount of data that we can use. So this is an issue, high quality, and how we qualify that, right? So, and the third is models, machine learning models, which always in some form or the other use deep neural networks. Means whether it is a multi-layer perceptron, or whether it is a convolutional neural network or a transformer, all these are deep learning models. And these are in some form or the other used in these big advances that you are going to see here, or that you have seen here. But the point is, all these neural networks, or architectures based on neural networks, models based on neural networks, they essentially at some level, by resizing or reshaping, perhaps they take a tensor or a matrix, at the end of it you can reshape it to a vector, and essentially they take a big vector, could be a humongously big vector, and they churn out another big vector which is very, very large, right? So at the end of the day, all these three, these we can use, the compute, data we have to think, and neural networks, which have been responsible for many of these big breakthroughs. There's an obstacle in the fact that inputs are finite dimensional, probably very high dimensional, and the outputs are finite dimensional. Whereas for us, remember that ideally my inputs and outputs have to be functions, right? Because after all, I'm going to approximate operators, and operators are mappings from functions to functions. On the other hand, the usual models in machine learning, these are mappings from very large vectors to very large vectors. So somewhere there is a disconnect, and we have to reduce, being mathematicians, we have to reduce our problem of input outputs as functions to input output as potentially very large dimensional vectors. So this is somehow the essence of operator learning. How we reduce essentially an infinite dimensional problem into something which will look like finite dimensional. Okay, so this is sort of the context, or this is sort of the setting that we are going to operate. So remember that at the end of the day, I have to reduce my infinite dimensional problem on a computer to something which is going to be finite dimensional. How do I do it? The first step, So the first step, let me give you the setting, and then let me make an approximation that will make things, I don't know how well, yeah, Bruno, what's going on? No, it's okay. Okay. So how to deal with this? Remember that I have this problem, which is infinite dimensional, but the available tools for me are sort of finite dimensional. So how do I do this approximation? How do I reduce something which is infinite dimensional to a finite dimensional problem? So here is the setup. So just for some notation, so we have two Banach spaces, and we have probability measure on the input space. There could also be a probability measure on the output space. It's not necessary. So we have a probability measure on the input space. We have an abstract PDE. So this is my PDE. This could be the standard second order elliptic PDE, Navier-Stokes, whatever you want. and then the solution operator, which takes the inputs. This could be initial boundary conditions, it could be coefficients. It takes the inputs in this infinite dimensional space, and it churns out an output which is the solution of the PDE, which is in this infinite dimensional space. So this is the infinite dimensional problem. So my first step, which is, people can think it's a very obvious or a trivial step, but it's a very important one, is that what if my measure here, so I'm sampling from my infinite dimensional input space, what if my measure here has support only in finite dimensions? In other words, instead of dealing with infinite dimensional inputs, I forget that and I deal only with finite dimensional inputs. Okay? And this is not such a dumb thing, because this is precisely the setting where we have parameterized PDEs. And I'm sure that this was introduced to you in the previous by the previous two lecturers, that you have parameterized PDEs. So here's a typical example of a parameterized. So this dy here, or this support of this measure, is precisely the set of parameters that the PDE has. So here is an example. Let me just qualify this example. So you have an airfoil. This is RAE 2822, a very standard airfoil, the one in black. And you want to design this airfoil, or you want to change this airfoil in order to, for instance, minimize drag at constant lift, or maximize the lift to drag ratio, or something like that. So what you do is that the equations are very well known here. So these are either the compressible Euler equations or the compressible Navier-Stokes equations, depending on the regime that you are in, or the regime that you are in. So it's let's say the Navier-Stokes equations. So you have the Navier-Stokes equations here, and you have some boundary conditions, some inflow boundary conditions, and then you have a shape across which the flow takes place. And this shape is always described by, it is of course in principle an infinite dimensional thing, because you can describe it in terms of a level set function, but in practice it is always described by finitely many parameters. And these parameters, I will come up with some specific samples later. For instance, in aerodynamics, these are what are called the Higgs-Henne parameters. So this one particular parameterization of airfoils. So this entire shape, or this envelope of shapes on both sides, these are described by anything between 20 to 50 parameters. So now I have my PDE, which is the Navier-Stokes or the Euler equations. I have I'm looking at steady flow, as you can see, means you only design in cruise conditions. So I'm looking at steady flow, and so you have space, 2 dimensions. You don't have time because it's a steady flow, but you also have these parameters. So you have anything between 20 and 50 parameters. Let's, for definiteness, stick to 20 parameters. So now my input here is going to be, for instance, the initial or boundary conditions, which are described completely in terms of 22 parameters, the 2 in space and 20 in parameter space. And my output, which is going to be, for instance, this is the velocity, or probably the Mach number, it looks like the Mach number. So you can see that this is an output which is now at each point in space and in parameter space, I have a function here. So in other words, my solution of the PDE now depends on, in general, on time, on space, and on parameter. And this is possible because I have said that the support of my measure, the input measure, is going to be finite dimensional. So these kind of parametric PDEs are very, very common in engineering and are a very, very common way to describe things, right? So if you are interested in the solution itself, that would be the setting, or you are interested in an observable of the solution, for instance, the lift and the drag, the integral quantities, then you have to integrate over space in some sense, and you are just left as a function of the parameters. So what have I done here? So in order to make this approximation from the infinite dimensional space, I rely on what is done in engineering practice, and I reduce it to something which is finite dimensional. So instead of having inputs, again I'm struggling a bit with, instead of having inputs, where are they? No? Okay. Maybe I should be here. Okay. So instead of having inputs, for instance here, where it's a mapping from a function to a function, I am in a situation where I can do mappings which are from, which are from essentially finite dimensional objects, parameters, to finite dimensional objects, which is some number here. So I've broken my infinite dimensional problem to a finite dimensional problem, and I started it on purpose because I believe that this was already introduced to you in some of the previous lectures. Once I have this setting, then I can use the fact that deep neural networks are mappings between finite dimensional objects and finite dimensional objects, and then I can use them to approximate my flow field, for instance, or my observables. So is this point clear? Because this is an important point, that you start with an infinite dimensional problem and use the natural parameterization, which is, for instance, given to you by engineering or by physics, and then you reduce it to a finite dimensional problem. And then you want to approximate these parameters by using deep neural networks. Okay? Any questions? No? Okay, fair enough. And all of us know what deep neural networks are, so this is my notation for them, because they come up again and again and again. So this is my notation for them. Neural networks are just, for me, mappings which take an input and pass them through different functions which are composed to each other. So this is a concatenated composition, and each of these sort of elementary functions is either an affine map, which is here, or a scalar nonlinearity, a pointwise nonlinearity. So the affine map is a matrix multiply. This guy is a weight matrix, and you add a vector. So this is what is called a bias vector. And these guys here are my tuning parameters, which are in some big tuning parameter space. And here, sigma here is my activation function, pointwise nonlinearity. The common ones are ReLU and hyperbolic tangent. You have seen that in earlier lectures. So this is going to be my model. It's a very straightforward model. I just take affine maps, compose them with nonlinearities, affine maps, nonlinearities, affine maps, nonlinearities, and there is some readout at the end. So this is a very, very simple model. But now the way in which they are going to approximate my solution here, my parametric solution, is from data. So I will use data, and using the data, I'm going to approximate them. And the way I draw my data typically is that in my parameter space or in my input space, I take some measure, I draw things IID, so from my uniform distribution, I draw them. So these are the uniformly distributed ones. There could be some noise, but let's look at the noise-free setting here. So this gives me the ground truth. So for each of these data points, I'm going to use either a traditional numerical solver or some experimental observations, if I have any, measurements, if I have any. This will give me my ground truth. And now I will also evaluate my model at those points. A priori, there is no reason why these two things will match. So now what I'm going to do is I'm going to choose my tuning parameters in such a manner that this objective function here, this loss function, is going to be optimized or is going to be minimized. And this minimization can be done in the way that you want. In machine learning, it's very common to use some version of stochastic gradient descent, but other people have other choices. I think Jin Shao is somewhere in the audience, and he prefers a greedy algorithm. So there are different choices that people can make, right? So this is left to you. But the essential point is we need data, which is provided by, for instance, numerical simulations. We need a model, which is provided here by simply a multi-layer perceptron, a fully connected neural network. We need a loss function, which is given here, just a LP, L1, L2 type loss function. It could be something else, cross entropy, for instance, for classification. And we need an optimizer, which is also something that is, so at the end of the day, it's a very, very simple process. So you generate the data, you have your model, you optimize it, and you end up with some result. But the question is, does this work? And I'm sure that you have had a lot of discussion of whether this works or not. Okay, whether this works or not from Jin Shao's lectures. So let me just give you my 2 bits on it. So in principle, yes, this kind of a setting where everything is finite dimensional should work, because in principle, neural networks, even shallow neural networks, these are universal approximators. What it means is that as long as my map is measurable, it's anyway a finite dimensional mapping. As long as this is measurable, there is always a neural network that is going to approximate it to the order that you desire. So this is a basic fact that neural networks are universal approximators. However, in order to sort of quantify this error, there are many, many other elements. So in general, a very, let's say, rough breakdown of this error can be in terms of what are called approximation errors, generalization errors, and training errors. So approximation error is what, for instance, the universal approximation theorem targets. It does not give you a quantitative statement. For getting a quantitative statement, you need a little bit more context, a little bit more assumptions. For instance, if your map is Sobolev regular, means it has integrable derivatives of certain order, then the approximation error, it's not hard to show by various people. The size of the neural network to get this approximation error, this is going to scale in terms of the regularity. So, more regular the map is, easier in principle it is to approximate. Approximation error is essentially a worst case, or in principle, let us say approximation. On the other hand, there is also dimensionality. This is the dimension of a parameter space. So, remember in this aerofoil example, I had what was the dimension between 20 and 50, and S in that case is at best 1. It's not very regular, so it's at best 1. So, in that case, what you get is that this is a very, very bad number. It depends exponentially on the dimension. And because it depends exponentially on the dimension, this whole process has a curse of dimensionality. So, in general, we know this, that whenever we have high dimensional objects and we are trying to approximate them, in principle, you could have a curse of dimensionality. However, there is a little bit more input that we have. In particular, we know that we are not some generic Sobolev regular maps. These are solutions of PDEs. So, there is a lot more structure that you can use. You can use elliptic regularity theory, you can use analyticity, you can use some more regularity, and then there are lots and lots of results which say that this curse of dimensionality, this can be broken, this can be alleviated. So, in other words, for instance, let us take nonlinear hyperbolic PDEs and scalar hyperbolic PDEs. So, you can show that this approximation error, at least, it does not grow exponentially in dimension. It grows depending on where your, let us say, where your problem comes from. It grows either linearly or quadratically. For elliptic PDEs, this grows only as a log of the dimension because there is so much of regularity. So, there are lots and lots of results like that. I am just putting some of them here. There are many, many more. So, in principle, the map can be approximated with relatively small networks rather efficiently. That is the basic idea. But there are other sources of error, as I said. So, one of them is generalization error, which is essentially coming from the fact that this guy here, the loss function, is a discrete quantity, whereas the population risk is a continuous quantity. So, then you need to use some statistical learning theory, and usually one can prove, I will come to this point later when I am talking about operator generalization, that this error, it scales in the following manner, that it scales essentially like 1 over square root of the number of samples. And because it is 1 over square root, so 1 over square root is not so good, because if you want 1% error, even if the numerator is 1, which is not the case, but let us assume that the numerator is going to be 1, then because there is a square root here for 1% error, which is 10 to the power minus 2, you see that this will be 10,000, right, because the square root of 10,000 is 100. So, you need 10,000 samples, which can be very expensive depending on what problem that you are looking for. For instance, just imagine that this particular problem, to generate this takes me about, depending on the resolution, means it takes anything between 2 minutes to 30 minutes, and if you have to do it 10,000 times, it is a lot of samples. So, this is something that I touched upon, which was that there is a data issue here, and this somehow exemplifies to some extent the data issue. It says that you need a lot of data in order to get at least good in sample generalization, and we may not have that much of data, because each of these data points is an independent solve of the PDE, and we do not have this much of data points, right. So, this is just telling you something, that there is a red flag here already with this error, and then this error, the training error, optimization error, this is a much harder nut to crack, because now the optimization is done over a very high dimensional space, a non-convex loss function, non-convex target, very complicated to get rigorous results, and there could be errors that are floating in here. So, what does this slide tell us? The slides tell us that in principle, if everything works well, if you have enough data, then this approximation of this finite dimensional problem should work well. But in practice, you do not have enough data. Okay. In general, you do not have enough data. So, you have to stick to moderate data, which is, can we do the same sort of an approximation? Can we get 1% error with, let us say, instead of having 10,000 samples, 100 samples, or 1,000 samples. So this is often the challenge. Okay? Are there any questions here? Means this is quite a lot of things to swallow. So yes, please. Yeah, you can start.
Yeah. So here you go back to finite dimension by saying that you have sampled during space. But can you develop the same?
He's loud enough. Otherwise, I can also. No. I'm sorry.
Yeah, so I was saying here you go back to finite dimension by assuming that you have sampled your input space with some parameterization, for example. And therefore you got universal approximation theorem and all of the theory in finite dimension. But could you develop all of this in truly infinite dimension?
You have to wait. Yes, the answer is yes, but this you have to wait a little. Okay, I will talk about it at length later.
Okay, thank you.
Okay. There was another question. Yeah.
Hi. I think I didn't catch some parts of the definition for it. I wonder what is the sigma AF means, and also what is the CEM there?
Can you repeat that? I lost you.
Oh.
Sigma of what?
Sigma. Is it sigma F there? The from the total error there.
From the total error.
Approximation.
Here?
Yeah, the arrow there with the APP there is a approximation.
This one here?
Oh, epsilon. I'm sorry.
Epsilon. Epsilon is always the error. Yes. So in order to get an error of size epsilon, the size of a neural network, it's both. I put both the depth as well as the width in the same. There is a very clear depth and a very clear width, but I put them in the same bucket. You know, to get a size of epsilon, the size of your neural network, which is given in terms of its depth and width, it grows in this particular manner. Okay. So you can do it the other way around also. You can say that what is the epsilon as a function of size? You just have to invert this equation. So this is a clear sort of a quantification of the total size or degrees of freedom, if you want, in order to obtain a certain amount of error.
Okay, thank you. And I wonder what is CM there in the
CM. I push too many things, right? So CM depends on the size of my neural network. So M is roughly the size, as you can see here. Also, there is a M. I was too quick, but that is not my main objective. So this is a constant which depends on the size of your neural network. So of course, if you have a large enough size, then your n has to be much larger than the size, because statistical theory is always for an under-parameterized regime. But the C, some people call it as the compressibility constant. So this tells you that even though m could be very large, C of m in practice is a very, very small number. So you can estimate it from the data. So for instance, m could be 10,000, but C of m is 10 to the power minus 2 typically in practice. Okay, so that the whole thing becomes order of m. Yes?
There is a question online. So concerning the error due to the sampling, EPS train, I guess, epsilon train, I guess it depends on the way that the sample is performed. Could you comment on that?
Sampling is all, I started with this assumption that I'm doing random sampling. So I take a distribution, I take a measure on my input space, which is finite dimensional, and then I just sample randomly. And because I'm sampling randomly, I can essentially use statistical learning theory, some concentration inequalities, and so it's random sampling.
Yes.
Okay.
But perhaps it is random according to a certain
probability
measure that you have to decide.
Yes.
So perhaps it is the question.
Okay, I see. That's a good interpretation. So it depends on, you have to put in some model for your data. So it's always the case, you have to put in some model for your data. Usually in engineering applications, you don't have a prior, so you put uniform distribution as the typical one. I see. Good. Thanks for the interpretation. Well, good that things get a little bit more clear. Are there further questions here in the room? Or online, I have to rely on you people to interpret for me because I don't see a thing. Oh, yes.
So, good morning, and I have a question about the abstract PDE. And how do we encode the information of the PDE as input to the neural network? So
in this particular case, the regime that I'm talking to you so far, you don't encode it. So it is blind to the PDE. Okay. Later on, you will see that the PDE also comes in, but that's a very, very good question. So you have taken the PDE out and you have reduced it to what we call a regression problem, or it's just a data matching problem. So here the PDE only comes in through the data itself. Means this guy comes from the solution of a PDE, but I am not putting any particular priors, or also maybe perhaps it's important to say it's a very good question, because in order to prove any of these results here, you need to realize the structure of the PDE. So in that sense, but algorithmically you are not using the PDE at all. Okay. And in fact, it's a very, very good question. I will discuss this at length later on.
Thank you.
Okay, so perhaps are there any further questions? If not, let's also thanks to Vitorita and Bruno for moving around with the mics and for interpreting the questions. So this is the setup that we are in. So in principle, this finite dimensional problem we could solve if we know how to deal with moderate data, because in general otherwise there's a lot of data that we need. One thing that we can do is, this is a problem in numerical analysis essentially, right? So there is a whole bunch of tricks that have been known in numerical analysis to deal with this sort of data problem, because unlike in traditional machine learning, our data does not come from, let's say, images that we are taking on the street or text that is taken from Wikipedia. This is generated by us usually. It is generated by us, which means that we have some control on what is the distribution that we can design from, what is the distribution that we can sample from. So in particular, I'm struggling a bit with the wireless for some reason. Okay, in particular, you could, for instance, instead of taking random points, which is what people usually do in machine learning, this is the assumption, you could take a more curated version of points. For instance, Sobol points or what are called low discrepancy sequences, right? So for those of you who know numerical analysis, a replacement for Monte Carlo is quasi Monte Carlo. So quasi Monte Carlo is where instead of taking random points, you take quasi-random points such as Sobol points. Now the idea here is very, very simple. So I'm just doing points on a sampling points on a unit square, and the random points, Monte Carlo, they are in blue, and you can see that they're not very well spread. They're random points after all. In particular, if you take some of the small squares that I've divided the unit square in, for instance, they don't have a single of the random points, right? A single of the blue points. On the other hand, quasi-Monte Carlo relies on these low discrepancy sequences where you have points that are better distributed or equidistributed as they are called. So for instance, Sobol, the orange points, you can see many of these boxes have, or almost all of these boxes have a orange point in it. So because they are this well distributed, they have been specifically designed to be equidistributed. One can prove, and this was done 3 years ago almost, that one can prove that the total error is now. So what I'm saying algorithmically is that instead of doing random sampling here, my sampling is done using, for instance, the Sobol points. So the total error depends on the training error, over which I have no control, but I can check a posteriori. It depends on some constants which are based on what is called the Hardy-Krause variation. So these are essentially mixed partial derivatives, and there is a logarithmic correction, which means that my dimension can't be more than, let's say, 20, 50, something like that, and it's now linear. So earlier this was a square root, so I needed 10,000 samples in order to get 1% error, but by just doing this sampling, I can reduce it in principle to 100 points, right? 1 over 100 is what we needed, and n can be 100 points. So this is one particular trick that you can use, and there are many such tricks, right? So you already know in numerical analysis that we don't need to sample from random points. We can sample, for instance, from quasi-random points. If it's 100 dimensions, you can't do anything. Then you really have to rely on but many of our problems are not in 100 dimensions. They may be in 8 dimensions, 12 dimensions, 20 dimensions. Then you could use tricks like that. Another trick, many people use it, is multi-level training. For instance, in this paper some years ago, this was done. So multi-level is that when we generate data with numerical simulations, we don't necessarily have exactly one grid. We have some coarse grids, some finer grids, fine grids, and so on. So if you take a lot of samples on a coarse grid, it's cheap. Or if you take few samples on the fine grid, it's still cheap. And then you somehow combine them. And by this, you can also reduce this bad dependence on the number of samples. The details are not important here. These papers, there are many of them these days. So there are numerical analysis tricks that you can also that you can do in order to sort of solve this data problem. So there are as I said, and on the training algorithm side, I think maybe Jin Shao spoke about it yesterday. Again, I'm suffering. There are greedy algorithms which can reduce the training error. So this error can be reduced by these kind of tricks that I just described, and so on. So in principle, we should be able to solve this problem, and this is also in practice there is some evidence for that. So for instance, the same problem that I said with the airfoil. So as I said, for a very high resolution, it takes about 40 minutes. This is a very high resolution. You probably don't need that much of resolution, but let's stick to that. And if I do this with exactly 128 training samples, I have used this sort of quasi-Monte Carlo or Sobol sampling, then I can train my neural network. It's a very small one, only 10,000 parameters at most. It takes very little time to train, and the evaluation time, the inference time is very, very fast. In particular, if you're interested in drag and lift, this is a microsecond or 10 microseconds. And if you're interested in the whole flow field, it takes about 1/10 of a second, and the errors are still acceptable. So this is completely a parametric problem. I have 20 parameters that describe the shape of the flow, shape of the airfoil, and then I'm interested in predicting, for instance, the density and the pressure and so on and so forth. So this is an example where a parametric problem has been successfully solved using the framework that I just suggested. Here's another example, maybe arguably more important. So this is, we are in the Mediterranean. So there can be earthquakes. There have been in the past. There can be earthquakes. They're usually in the fault, which is just located off Crete. And once there is a reasonably powerful earthquake, there's always a possibility of a tsunami. And this entire process here is modeled by two things: the flow itself by shallow water equations, hyperbolic PDEs, classic hyperbolic PDEs, and the initial conditions. So when the earthquake happens, how the sort of deformation of the ground under the sea results in the initial waveform. This is by a model called the Okada model. Took many, many years to design, 20, 30 years to design. It tells you how the sea flow deformation can be modeled into initial conditions. And this, once you have the initial conditions, you solve the shallow water equations, and you're interested, for instance, at different points, how the waveform looks like. So this is the wave height as a function of time, and you can see that with a traditional numerical method, even a state-of-the-art method, it takes about an hour, and an hour is too long. But if you use neural networks exactly in the setting that I just told you, in a parameterized manner, the parameters, there are 11 parameters here given by this Okada model, then the whole thing can be done in 1/10 of a second. And as you can see, that even the most inaccurate prediction here is fairly accurate. So in some sense, another example where this entire sort of, let's say, machinery, it really works. And once you have this, once you have these kind of predictors or deep neural network surrogates, you can use them in downstream tasks. There are a variety of downstream tasks that you can think about. So one of them is, of course, uncertainty quantification, a very prominent downstream task. So for instance, instead of just finding the lift as a function of, as one instantiation, one instance, one sample, you vary the flow conditions, for instance, the Mach number and the angle of attack and so on. There is some uncertainty in them. And how does the distribution of the lift change? How does the distribution of the drag change, and so on? In other words, your measure, which was parameterized by finite dimensional quantities, how is it pushed forward by the map the ground truth that you are interested in approximating. So once you have a good surrogate, well-trained surrogate, all that you do is that instead of computing the statistics based on the PDE solver, you take a few samples, you train your PDE solver, you train your deep neural network surrogate, and because it is so cheap to evaluate, you can use thousands of samples in order to compute the empirical distribution, for instance here. So this is a very trivial use, downstream use of your surrogate, of your deep neural network surrogate. And there is a tricky issue here, because all that I'm interested is in sampling. So of course, if I have 1,000 training samples, I could also use them for my Monte Carlo calculation, right, of the uncertainty. So here you really have to use less number of samples, like 100 samples, for instance. And with Monte Carlo, you see huge amounts of speed up. Also with quasi-Monte Carlo. Now, quasi-Monte Carlo is state of the art for these kind of problems. They don't have the regularity to do, for instance, GPC as an example. Then you can see that even there, it's an order of magnitude speed up. And if you do multi-level, there is another factor of 3 to 5. So you gain something like 50 over a traditional numerical method. Let's put it that way. So this is one example. Another example, which is downstream. So these are different downstream tasks, is of course design or PDE constraint optimization. So again, instead of using your traditional numerical algorithm, you just use the trained neural network. There's a little bit of a active learning algorithm, some innovation here. It's not a straightforward copy, but you can do it. I am not going to describe the details. So for instance, this is the original shape, and you change to these shapes in a sort of a automatic manner, in a PDE constraint optimization manner, and the drag is reduced by, the lift is the same at constant lift. The drag is reduced by 50%, so means that the lift to drag ratio is considerably increased. And the main point is with this new algorithm, which is based on this deep neural network approximation, what you can see is that in my classical algorithm, it took me something like, let's say, 2,000 samples, 2,000 evaluations of my PDE to get my drag down. And now I can do the same with anywhere between 50 and 100 samples, because I need to train my algorithm. So again, you get a speed up of approximately 20 to 50. So once you have this training, then you can do this, let's say, downstream tasks. And if you do Bayesian inversion, there you have even bigger payoffs sometimes. So the bottom line is that by reducing the problem to finite dimensions, by using the properties of the PDE itself, and by, let's say, innovative sampling, and by smart algorithms, we can do quite a lot. However, there is always a catch, right? And this was already, let's say, attributed to a little bit before. Oh, sorry. So where is the catch now? So this is the key point. So the catch is, and this I will spend a bit of time on the slide because it's important. So far what I did is what you've probably seen before. It's sort of finite dimensional. Everything somehow seems to work. However, the approach that I suggested, it relies on the availability of good parameterizations. Someone has to give you the parameterization, or you have to design the parameterization yourself. So for instance, in the examples that I showed you here, the parameterizations have been done by engineers for 30 years, means these Higgs-Henne parameters have been around for quite a long time. Similarly, for the tsunami application that I showed you, this is again 30 years it took for someone to come up with the right kind of parameterization. So there's a lot of, let's say, engineering know-how that has gone into these kind of problems. So in order to do this parametric approach, the most important thing is that we need a good parameterization. If we don't have a good parameterization, for instance, from this expert knowledge, then we need some explicit information about the underlying measure. You remember that at the end of the day, I had a probability measure on a function space that I said was supported by finitely many parameters. So in practice, this requires a lot of expert knowledge. And this is not always available. And if you have a new application, then you don't have this available. You only have access, or you can probe the measure through sampling, and that's about it. But there is an even bigger problem, and this is where I would like to sort of make an important point, that what I had spoken about does not generalize. Now, what is generalization? Means this is a term that is often bandied about in machine learning, and it has different connotations for different people. So for instance, this is something called in-sample generalization, which was described by me somewhere here when I computed the generalization error, which is that you're drawing from a distribution, but you don't have access to the entire distribution, you only have access to samples of it. So what happens when you go to unseen samples which are drawn from the same distribution? So this is what is called in-sample distribution, and the error there was somehow controlled by this quantity here. So this is, many people try to understand this, but machine learning is not just about that. It is about what is called out-of-sample distribution, means things that are really unseen, not just dogs and cats, but wolves and tigers in machine learning paradigm. Let me explain it to you. So here is an example. So this was my problem with the airfoil. As before, I have 20 Higgs NA parameters, and this is how the flow looks like. Now what if I change the number? So now I train my neural network based on this 20-dimensional input. I take this 20-dimensional input and I produce my output. What if for some reason, means there could be various reasons, maybe I have more manufacturing fidelity and I change my number of parameters to 30. Now if you look at the shapes, they don't look very different from each other, whether I take 20 or whether I take 30, they're not very different from each other. But now boom, you can't do anything. Remember what I had done? I had taken my inputs to be 20 dimensions in parametric space and 2 space dimensions. I had trained my neural network to give me a 4-dimensional output, pressure, velocity, and density, and so on, right? But now I changed my input to 32 dimensions. The shapes are very, very close to each other. Let alone do anything, I can't even evaluate it anymore, because I had fixed my number of parameters, I had trained my model, and now boom. And in fact, you can be much more severe than that, because you have a measure, you have evaluated it in a certain number of parameters, you can reparameterize it. Let's say I have evaluated something with 3 parameters. I can always reparameterize it by, let's say, 6 parameters. Nothing should have changed, right? It's the same measure, I have just a different parameterization. Again, this approach tells me I can't do anything, because I have fixed my number of course I could have used a different architecture with input dimension which was different. But the setting that I showed you so far with all these nice pictures and all these nice theorems, that fails completely, because I have no way in which I can deal with a different parameterization. So not only do I need a parameterization, which might be difficult to evaluate, but because I have a parameterization, I cannot even deal with a situation where I change the shape ever so slightly, but perhaps by a few more number of parameters, and then what do I do? And so I'm stuck. Okay? So this is what I, in some sense, at least one connotation of generalization. There are different connotations that will come up in today's lectures, but this is one important connotation. So here is precisely the point where so far, whatever we have done, it was useful. It is useful in an engineering context, but it is by definition or by its nature rather limiting. At some point, we have to go beyond it, and we have to really learn genuinely the operator rather than just a finite dimensional parametric representation of it. This is a point that is very, very important, because otherwise I will not be able to deal with this situation here, where I go out of distribution and try to find something and evaluate something out of distribution. And this is a very, very important point in machine learning, because machine learning is about new things, not just about fitting the distribution that you have. It's about learning something about what you have not seen before. Okay. So at this point, I would like to take some questions. I already see one hand raised, so, and I try to also drink some water.
But this operator learning could not actually solve the issue that if you change the input dimension, you have to retrain again, right?
It will solve it, because my entire, you'll see, because then my input and output will be infinite dimensional.
Okay. Thank you.
So you'll see, that's the whole point. Further questions? No? Yeah, Olga. If you shout and then I shout back your question, maybe.
At the end of the day, in your approach, don't you need some compactness in your input space to do something eventually?
You'll see that.
To enter it into a computer,
You'll see that.
I don't see any other way as finding some parametrization which is maybe going to be invariant to translations, rotations, or... You are hitting the nail on the head, but you are anticipating what I'm going to say. Oh, sorry. I was just intrigued because otherwise I wasn't seeing the way out.
Of course, this is a very valid point.
Thank you.
At the end of the day, you have to deal with finite dimensions, means you don't lose that. But you'll see, you have to be a bit smarter than just taking some input dimension as a given. That's all I'm trying to say.
Thank you.
Are there some questions on the chat or no? Okay, so this is a good point to move on. After setting this, we somehow still need to aim for genuine operator learning, which is that my inputs and outputs have to, in some sense, be infinite dimensional. At the end of the day, I have to do approximations. There's no way I can put infinite quantities on a computer, right? So you'll see that's how to do it, or one possible way to do it. Okay, so remember that this is the setup. So I have Banach spaces. Later on, I will simplify to Hilbert spaces, but for the time being, let us take Banach spaces. I have my abstract PDE. A is my input, U is my output, F could also be my input, but it depends on what I want to do. And this is my solution operator of the PDE, and I want to learn this from data, right? So this is the setup in which I am operating. Now, remember that I need to do genuine operator learning in the sense that I take infinite dimensional inputs. I don't use a parametric approach the way I have done it so far. So there is an obvious solution to that. It's fairly obvious. This is the second solution, another approximation, and it's a fairly obvious solution, but it has its own set of problems. So let me give you the let me explain it to you by an example. It's always an example is worth 1,000 words, right? So picture is worth 1,000 words, but they have the same meaning. So here is my solution operator. I take the Navier-Stokes equations in 2 dimensions. In the vorticity stream function formulation, for instance, my solution operator takes the initial vorticity, which looks like this, and then it churns out the final vorticity, which looks like this. So this is a map that I want to approximate, take the vorticity, and churn out the vorticity. This is a very common example. I have my issue with this example, which I'll come to later, but let's keep this as an example. This is a bona fide solution operator. For instance, it takes vorticities which are HS, and it produces vorticities which are also in HS. In 2D, there's no vortex stretching, so you can do this, no problem. Now, how can I do this in a sort of a genuinely operator learning approximation instead of parameterizing? So one obvious solution is the following. So what I do is I start with my input, which is an infinite dimensional object. It's a 2-dimensional object, which is defined. It's infinite dimensional as a function, but it's defined on a 2-dimensional domain, a unit square. So what I do is I put some points in the square, let's say for simplicity, just a uniform discretization of the square. And I sample this on each of these points. Okay? So instead of having a function, I am changing the function to a discrete representation, which is just point values of the function. If my function is a continuous function, I can always do that. Now once I have this, so remember that instead of having a infinite dimensional input, I have reduced it, or I have projected it down to something is finite dimensional, but of course a very large number of dimensions, because already here you can see that this is 16 times 16, so 256 dimensional vector. So instead of having a function, by sampling it on points, I have a 256 dimensional function. And then, for instance, what I could do is, if I used a MLP, a fully connected neural network, this could be very, very large, right? Because then each point has some weight. So in order to get some notion of space, some sparsity, let's say, I use a convolutional neural network. So roughly speaking, I'll come to some details of convolutional neural networks in a bit. So roughly speaking, what I do in a convolutional neural network is that I take a kernel. I don't see, yeah, you can even see the kernel. A kernel, and then I just sweep through different parts of it. Of course, I increase the channels, the number of, let's say, variables, I increase the channels. I sweep through this, I increase the channels, sweep through again, increase the channels, and so on. And this gives me a neural network representation from this 256 dimensional vector, or let's say 16 times 16 dimensional matrix, to something which is also, let's say, 256 dimensional vector. So now I take my function, I just look at its point values, process them through a convolutional neural network, and I get another representation of the output through the point values. But of course, if I have the point values, I can always interpolate. Okay? So I can always interpolate, for instance, by using piecewise linear interpolations. So if I wanted to process functions to functions, so what did I do? I sampled them on a grid, used a convolutional neural network, and then the output is also sampled on a grid, and I can always reinterpolate in order to find the value at any point, function to a function, right? So this is in a way you can call it as operator learning, because in this case I took a function, I just sampled it on a grid, processed it, and resampled it back to infinite dimensions, for instance, by interpolation. Everyone agrees that this is a very simple way of dealing with a function to function map, right? So this is one potential way, and in fact this is a way in which people dealt with let's say solution of PDEs to some extent. So in other words, sorry about this, yeah. So let's take an example where we see how this works, okay? So this is a slightly more complicated example because I sort of like it. It's you can call as incompressible Euler equations or Navier-Stokes equations with very high viscosity. So you have been given a velocity field here, and the solution operator takes the velocity fields and it produces as initial conditions, and it produces the velocity fields at a later time. For instance, t equal to 1. And to see how the flow develops, it's easier to work with the vorticity. So this is a vortex layer or a vortex shear layer as it is called, and after a while the vortices is shed and you get a solution which looks like this. It is not the easiest problem to solve, and in fact our standard incompressible Euler incompressible Navier-Stokes codes in 2D are benchmarked on this particular problem. Now I do this, I take inputs and outputs, don't ask me how many samples I used. Don't understand this at all, why this works. Don't ask me how many, I think about 1,000 samples, right? We probably used about 1,000 samples to train this, and then you see that, and this is done on not on 16 squared, because 16 squared would be too coarse. I do it on 64 squared. So the resolution at which the sampling is done is 64 squared. So if I do that at 64 squared, I see that the error is about 5%. Okay, 5% is 5%, means let's not split our hairs about it. However, remember that my objective was not to learn a map from 64 squared to 64 squared, right? My objective was to learn a map from the function space to the function space. So how do I do that now? So it turns out that I can actually evaluate my trained neural network, the convolutional neural network, details will come in a bit. I can evaluate them on any grid, essentially, because convolutions are discrete objects, and I can sort of evaluate them on any grid. In particular, I can evaluate them on a 128 times 128 grid. I can evaluate them on a 32 times 32 grid, and even smaller than that. But in this particular case, I've evaluated them. So if I have learned the underlying operator, which takes a function to a function, then I should get errors which are reasonable when I change the resolution also. And this is precisely what doesn't happen. So if I take, for instance, 128 squared by 128 squared grid, I can evaluate my convolutional neural network, and it gives me 20% error. And similarly, if I take a coarser grid, 32 by 32, again I get 20% error. So in fact, almost immediately the error jumps, which tells me that what this entire process has learned is not the function. It has learned a particular discrete representation of the function, which is its sampling on a 64 squared times 64 squared grid, or its input output map from a 64 squared grid to a 64 squared grid. And this is not my observation. This has been known for a while. For instance, Nick Sabaras was probably the first to observe it. Many people have observed it, and so on. So this tells me that this obvious solution, where you can just get away with just any finite dimensional projection or sampling, has its issues, because what you end up learning is not actually the function operator itself, but just a particular discrete representation of it. So it's not invariant with respect to discrete representations. So here I put some desiderata for operator learning, and in addition to the fact that the inputs and outputs are functions, which is of course the definition, I also want to some form of resolution invariance or discrete equivalence, or so on and so forth, so that I learn the operator itself and not just a discrete representation. Is this point clear? And this is a very, very important point. 10 minutes. Oh, you even have that. Okay, so this is a professional outfit. But this is a very important point that I'm trying to make here. And is this point clear? Because, right? So what do I mean? So you really need to learn the genuine operator and not a discrete representation. And by doing this, I'm just learning a discrete representation. So this is a very, very important element. Any questions about it? No? Yes, please. You have to be more professional, like in, you have to have mics in every row. Yeah, go ahead.
So one of my question is, so everything, all of this structure really works, where I see like there is a very nice regularity to the solution. But what I understand from operator learning is, does operator learning also entail learning the structure of the PDE? Also, like, how do we know that if a convolution neural network is learning from certain snapshots to a PDE, and it's spitting out a solution that is going to be physical? How do we ensure that?
Yeah, this is a good question, and I probably have some answers of it later. So you have to wait. I have not even defined properly what operator learning is. So, right? So I will answer your question afterwards. Any further questions? No? Okay. Let's just continue. So remember that I want to learn the operator and not just a discrete representation. And let's see what I have next, because now it's okay. And maybe we stop with this slide a little bit earlier than expected, because why is this a challenge? And I think Olga already referred to this before, that in principle, we want to learn maps between inputs and outputs functions, right? So this is essentially don't ask me what, I think this is the coefficient of a Darcy flow, and this is the flow itself, something very, very regular. But in practice, at the end of the day, on a computer, we have to deal with discrete objects, right? So whatever we do, we are never going to be able to input a function itself, or where we are going to output a function itself. We have to deal with discrete quantities. And not only that, there in practice, not only are they discrete, but there has to be some sort of a input-output representation, which will also be sort of variable. Or in other words, you could sample on different grids. For instance, this is the same flow configuration, as you can see, but the input and output map here. So you can see that this is sampled on a regular grid, on a uniform grid, and this is sampled on a completely variable grid. But they are both bona fide representations, discrete representations of the same object, of the same operator. So in practice, you can have multiple discrete representations. And as someone already commented, on computers, we can only have discrete representations. So now coming back to my desiderata, that I needed this sort of a invariance, or let's say equivariance, if you want to use a fancy word, with respect to discrete representations. This has to deal with the challenge that there can be these multiple discrete representations of the continuous quantities that we're interested in. In other words, what we really need, and what I'm going to do after the break at some length, is a proper notion of continuous discrete equivalence. Okay? So continuous discrete equivalence means that I have some underlying continuous ground truth is a continuous quantity, but in practice I have to deal with discrete quantities. What is the relationship between them? In particular, I would aim for equivalence so that the entire structure is preserved. In numerical analysis, you can say, why do you aim for equivalence? You can do approximation. This is a valid point. But after all, we do structure preserving discretizations and so on. Bruno has done it himself, for instance, right? So we want to preserve this, and we want to introduce some notion of continuous discrete equivalence. So after the break, I will show you one particular notion of continuous discrete equivalence and how this can be leveraged, how this can be harnessed in order to do operator learning, and how by using this we can develop different kinds of operator learning algorithms. So I take 5 minutes before. Can we also start 5 minutes before as a consequence? Okay, so let's when do we start now?